And now for our first practice problem. Let's imagine we're creating a neural network to identify spam email. The network's input layer receives email features such as frequency of specific words, sender reputation, and usage of exclamation marks. The hidden layers must discern patterns. What combination of these features typically indicates spam? And the activation functions at each neuron in these layers will decide whether the pattern is strong enough to consider the email spam, influencing the final output spam or not spam. So to go over, we are doing a neural network. Okay, come on. For spam, email. When doing so, we have the following for a neural network: input, layers, and output. And as we know, that every single neural network's neuron that we have already set up in place is going to have weights, biases, and activation functions set in place with an optimization algorithm. And to go over what we just discussed, so for our input layer, if we were going over the specifics of the layer, since that is where the training process happens, the input layer for one is going to set the features and the hidden layers will discern patterns, which combination of these features typically sends spam. So ultimately discerning features and the activation function at each neuron in these layers will decide whether the pattern is strong enough to be passed from one layer to another. Determine if pattern is strong enough to pass per layer. Hang on one second. There we go. And so let's just go over the following steps that we need to be able to construct this. Step 1, input layer configuration. Step 2, design the hidden layers. Step 3, choose activation function. Step 4, train the network. And those are our steps to do. So when we input the layer configuration, we begin by setting up the input layer with neurons equal to the number of features we've identified as significant. So we identify significant features. Each feature of, for instance, an email, such as a text length or a number of hyperlinks it contains, is fed into the respective neuron. So features are fed into respective neuron. And the step is critical as the quality of input directly impacts the network's ability to learn effectively. The second part, next we need to configure the hidden layers, which refer to the number of layers and neurons per layer require careful consideration, as this architecture will capture the complexity of our problem. We must strike a balance where too few neurons may not capture the nuance of the spam, while too many neurons may lead to overfitting. So we need to consider number of neurons for few neurons inaccurate. Well, I mean, they're both going to be inaccurate. Like, overfitting really is just making a wrong prediction based on those features, given the fact of the data that it's specifically trained on, hence overfitting. If we were to have an untrained piece of data fed into the neural network, it would categorize into completely something else. But it's just been so well trained in the features that we have already set up in place, it's going to focus solely on those features. So that's what the premise of overfitting is. So we're fitting too well trained in features. In specific features. Or too few, not, so few neurons are not able to categorize spam. Or whatever context you want to put it. The third part, choosing an activation function. Now that in this part we select an activation function for the neurons for a specific detector. In this case, we're going to be using the ReLU one. So yeah, so ReLU activation function could be a good choice for hidden layers due to the simplicity and efficiency. However, for the output layer, we might use a sigmoid function since our final decision is binary spam or not spam. So we could do a sigmoid for the sake of binary because there's always the most convention. So depends on context of problem. Context of problem. And what specifically you want to output. Want to output. And when we train the neural network in our fourth step, training involves feeding the network a large number of labeled emails. So we feed the network with large amounts of data. No. Of labeled data. All that data is labeled. And when we have done so, we would consider the weights and biases of the labeling. And well, but really the weights between the neurons are adjusted through a process through backpropagation during the training process. Weights adjusted during training, specifically in the step of backpropagation. Biases, on the other hand, are also considered as well, hence our formula. Well, the biases, on the other hand, where the biases can refer to bias in many factors. And in biases, we consider the chances of error, and can refer to data bias, selection bias, algorithm bias, accordingly. And now let me just move out so you all get an understanding. Feel free to take a screenshot of the steps. And let me just fix this part. And now let's go over the following steps for our specific program. So in this, what we will be doing is that, one, after we have loaded the necessary libraries for what neural network we'll be calling upon, how we're going to train and test and split, we call upon NumPy, Keras, and scikit-learn accordingly to be able to call upon the necessary libraries that already have these robust neural networks and tools needed to be able to actually train and then test a following model. So what we do first is that we load one data set. We have features from our data set that we consider in our X and our Y will be considered our labels. And since we're doing binary classification, we do 1 for spam and 0 for not spam. When we load the email data accordingly with respect to the features as well as the classification we're looking for, and we're doing a binary classification. We split the data set into training and testing, and it looks like we're going to do an 80-20 split that we have with a random state of 42 to be able to have a fair assessment of when we were training the following model. So then we scale the features for better neural network performance using scalars, standard scalar, and then we initialize the following model using a sequential model, and we have our layers that are over here, and it looks like, oh, must be the fact that we are using one hidden layer. We have our input layer. And then we have our optimizer. And we got our output layer. There we go. And we are fitting the model by training the model on the scaled training data after we have already trained our given model within the given layers, even if we're using one or more hidden layers. In this case, we're using one. And we fit with the trained scale and the Y trained with 100 epochs and a batch size of 10, verbose of 1. And we evaluate the model on the testing data as well to consider that, hey, is this model actually creating the necessary predictions? And then we set our predictions for the model to predict based on the features that we have in our test portion of our data set. And so, yes, feel free to take a screenshot of this part over here. And then feel free to take a screenshot on our left side as well. Let me just clean this up for you folks to get a better understanding. Feel free to take a screenshot of the coding assessment as well. And the whole practice problem. And now let's go over our second practice problem. And so yeah, thank you very much for taking time to watch this. If you found this video helpful, be sure and feel free to please like and subscribe. And if you have any other questions, feel free to put it in the comment section. And as always, take care. Cheers. Bye-bye.